Okay, so let's get started the second session. So the first we have the contributed talk from George Tucker on doubly reparameterized gradient estimators for latent variable models. So welcome, speaker.
Thank you all for coming. So this is joint work with Dietrich Clausen, Shane Gu, and Chris Madison. And in this work, we introduce an unbiased low variance and computationally efficient gradient estimator for training latent variable models. And we show its applicability to three recent training schemes for latent variable models: importance-weighted autoencoders, reweighted weight sleep, and jackknife variational inference. And in this talk, I'm just going to go over briefly the background on importance-weighted autoencoders. Then I'll talk about the doubly reparameterized gradient estimators and show some experiments. So in this work, we looked at the standard latent variable model setup. So we have latent variables z with and a stochastic mapping p of x given z that maps the latent variables to the data space. And ideally, we would maximize the log likelihood, but integrating out the latent variables is intractable. So we introduce a inference network Q, which maps from the data space back to the latent factors, and we can construct a lower bound on the log likelihood. And in this work, we'll just abbreviate the ratio of this importance ratio with W. And we typically estimate this expectation by drawing a single sample of Z and then evaluating the inside of the expectation. And what we know is that the tightness of this bound is controlled by how accurately the inference network can match the posterior. And typically, for some tractability, we use a simple family of inference networks, for instance, factorized Gaussians. And this can limit the learned models that we get. So in 2015, Yuri Berta introduced the idea of using an importance-weighted, multiple importance-weighted estimator instead. And the idea is, instead of drawing a single latent factor, we can draw multiple samples from Q and then average them inside the log and take the expectation. And we can show that this actually is also a lower bound on the log likelihood. And furthermore, we can show that it's an increasingly tight lower bound on the log likelihood. So as we increase k, we get a better and better lower bound, and we can show that as k goes to infinity, it converges to the log likelihood. So as k goes to infinity, the effect of an overly simplistic variational family diminishes, and this is very nice. However, in recent work by Tom Rainforth and others, he showed that there's actually more nuance to this. So what we find is that the gradient with respect to the inference network actually gets worse as we increase the number of samples. So in this plot, what I'm showing is the signal-to-noise ratio of the gradient estimator as we increase the number of samples in the highway bound. And the signal-to-noise is just measuring the mean of the gradient estimator divided by its standard deviation. So as we increase the number of samples, actually what we find is that there's less signal in that gradient estimator. And that's a bad sign for optimization. And Tom also showed that this happens theoretically as well. And so what we have kind of is this tension. So on one hand, if we have k samples from Q, we could just consider taking k elbows and averaging them together. And that would reduce the variance. And as we can see, it increases the signal-to-noise ratio as k increases, but that doesn't change the tightness of the lower bound. Alternatively, we could form the I-way-k bound, which is tighter as k increases, but then our gradient estimator is worse. So what we sought to do in this work was to resolve this tension. Can we come up with a gradient estimator for I-way that doesn't suffer from this poor degradation in signal-to-noise ratio as k goes to infinity? So now I'll go over this doubly reparameterized gradient estimator, which is able to achieve those properties. So starting from the typical I-way gradient estimator, we just use the reparameterization trick, and we get something that looks like this. And we typically use the single sample estimator of this expectation as our gradient estimator. And if we want to derive a better estimator, we can expand the total derivative here into using the chain rule, and we get these two components. And what previous work by Roeder et al. Found was that when k equals 1, this term is actually 0 in expectation, and so we can drop it, and this reduces variance, and so that's good. However, when k is greater than 1, it's unclear if this term is 0 in expectation, and actually we showed that it's not 0 in expectation. However, we could drop it. It results in a biased estimator, and Roeder et al. Showed that actually this works pretty well. So what we do in this work is show that we can actually estimate that bias tractably, and by manipulating a bunch of terms and applying some tricks, which I'll go over on the next slide, we can get a new estimator, this doubly reparameterized gradient estimator. And you can see it looks very simple. It's very similar to the original estimator. Here, instead of a total derivative, there's a partial, and the weights are squared. And this is actually really important. So in the proof that showed that the signal-to-noise ratio of the original estimator degrades, it critically used the fact that this estimator looks like a self-normalized importance-weighted quantity. So you have like these kind of weights that are self-normalizing, and then some kind of other function that you're taking an expectation of. And because of that, we get this degradation in signal-to-noise ratio. However, in our estimator, actually the weights are squared, and this makes all of the difference. This actually causes us to have increasing signal-to-noise ratio as we increase the number of samples. And I'll show some experiments later. So now, let me just focus in on this term. This is the key term that we looked at in our work, and I'll just show how we manipulate it. So critically, what we first notice is that you can just focus on one term of this sum. And then we can change the expectation we can kind of unreparameterize it. So go from epsilons back to the latent variables. And why we can do that is because this is a partial derivative with respect to the inference network parameters. And so it's not taking into account the dependence of z on theta, on phi. So we can freely change from epsilon to z, and then we can focus on this inside expectation. And then if we look at this term, it kind of looks like a reinforced gradient estimator term. You have something that looks like the gradient of the log of q, and you're taking an expectation over q, and this looks kind of like a reward term. And if we interpret it in this way, we can apply the reparameterization trick again here. And the reason why we would expect this to be better is because the reparameterization trick takes into account the gradient of this term, whereas the reinforced gradient estimator is more like a finite difference estimator. And then we can do some further manipulation, and a bunch of terms cancel, and magically we get a very simple estimator. It is a little bit surprising that we have to apply the reparameterization trick twice, and we kind of have to unreparameterize and then reparameterize. And I think that there's probably a simpler way to get at this, but haven't figured that out yet. Okay, so if we look at a very simple Gaussian system, we can see that as before, the importance-weighted autoencoder, if you take the gradients of the inference network, as you increase k, the signal-to-noise ratio is degrading, whereas our estimator is increasing. And we can also show theoretically that asymptotically our estimator is increasing as the SNR is increasing as you increase k. And if we look at a couple of other different metrics, we can see that our estimator has extremely low variance. It's unbiased, whereas sticking the landing, which was this other one that dropped the term completely, has some bias because it drops the term instead of dealing with it properly. But it worked really well, so. So additionally, we can apply this to reweighted wake sleep. And just briefly, reweighted wake sleep optimizes, instead of optimizing the KL from Q to P, it tries to optimize the KL from P to Q. And we end up with a term that's very similar to what we had in iWeight, and we can also use the reparameterization trick in the same way. And then finally, we can apply this to jackknife variational inference. And jackknife variational inference is this idea that we can take multiple different estimators at different K, and then combine them using a linear combination to eliminate some bias in the estimator. Because the jackknife variational inference is just a linear combination of importance-weighted autoencoder bounds, we can just apply the doubly reparameterized gradient estimator for each one of those terms individually. Okay, so now I'll show some experiments on MNIST and Omni-Glot generative modeling, and then finally some experiments on MNIST structured prediction. And you can see the paper for more specific details, but briefly it's just a 50-dimensional latent variable space, 2 hidden layers of tanh units and factorized distributions. And so we can apply this to the iWeigh, W-weighted wake sleep, and jackknife variational inference, and we see that in all cases, what I've plotted here is the gradient variance, and you can see large reduction in variance. And as you can see here, so the dotted line is the typical estimator, and then the solid line is the doubly reparameterized. And in all cases, we improve performance. Similarly for Omni-Glot, again, we see a big reduction in variance, and this translates to improved performance on the test objective. And we can also do this again for MNIST structure prediction. Interestingly, in this case, we see that sometimes reweighted wake sleep does better than importance-weighted autoencoder, but it's kind of problem dependent. And here is a case where using the biased estimator, sticking the landing does slightly worse than if we use the unbiased doubly reparameterized gradient estimator. But it's actually pretty problem dependent, and in some cases actually the bias sticking the landing estimator actually outperforms the unbiased gradient estimator. And understanding that better would be future work. Okay, so just to summarize, these doubly reparameterized gradient estimators are computationally efficient, unbiased, and they're drop-in replacements for the standard iWeigh gradient estimator. They rectify some of the asymptotic and practical issues raised by Rainforth et al. And we think it would be interesting to explore these further in other applications of variational inference to sequential models. There's a paper, slides, these slides actually on this website, and there's code for all the experiments.
So we have some time for some questions if there are any.
So is there a direct interpretation of the variation of distribution? So in standard VI, you minimize the KL divergence. You still minimize some divergence? Or?
Yeah, so this is more a question about, so we didn't change the bound, so we're still using the same importance-weighted autoencoder bound. We're just producing
so it's more efficient with it.
But yeah, there is an answer for that. There's a recent, I think, NIPS paper that talks about this extensively, but roughly, yes, you can think about it as expanding your space and then the iWeigh is actually a lower bound on the typical variational inference in this expanded space.
Point taken, you're not actually using the same VI.
So there is another question in the room? Oh. So I actually have a question. So I'm just wondering, does it have the same time complexity as the regular ID estimator?
Yeah, it's actually, yeah, it's the same.
Okay, but it's just better.
Yeah.
Okay, good.
It's fairly straightforward to implement too. So if you take a look at the code, you can kind of see like how we put stuff together.
Okay, good. Thanks. So can next speaker actually start?